Let's say recording. All right. Okay. So last week we talked about. Can you guys hear me on the back? Yeah. Can you hear me on the back? Okay. So last week we talked about damping. We add damping to the system. We develop the equation of motion. Just to refresh your memory and just do a quick recap. This is what we got, right? So we said the equation of motion has this form, mx double dot plus kx, or just to write them in order, cx dot plus kx equal to 0. So when it is 0, it means it is free vibration, right? No external force. Compared with the previous system, now we have damping, which we show it by C. That's a damping coefficient. Then we define some parameters. So we define omega n, which is a square root of k over m. We define C critical, which is 4 times mass multiplied by stiffness. And we define the ratio of damping C over C critical. So this weird shape, that's a Greek letter we call zeta or eta. You can Google it. What is the shape? Maybe I'm not writing it correctly. Or it is just Z. So the zeta is the damping ratio, which is C over C critical. All right? And we said this damping can have, this damping ratio can have 3 values. So this zeta can be bigger than 1, can be equal to 1, or it can be less than 1, right? When it is bigger than 1, we call it overdamped. And we said, in fact, there is no vibration. You disturb the system, it's going to return back to its original position fast. And then zeta is equal to 1 is at the boundary that behavior of the system is changed. So that's why we call it critically damped. So critically damped. All right. And then if zeta is less than 1, we call this one underdamped. We are mainly interested in underdamped because there is no vibration in critically damped or overdamped. All right. So for underdamped, after defining this equation, we wrote the standard form of the equation. So the standard form, which we divide everything by m, and we got x double dot 2 zeta omega n x dot plus omega n squared x equal to 0. That's basically the same formula. We just use the parameters that we defined and we put them, we simplify the equation, and we've got this new standard form. So if we solve this differential equation, you saw we get the characteristic equations, and depends on if zeta is bigger than 1 or less than 1, we get either real numbers or imaginary numbers. And simplifying those equations, if let's say our initial conditions, they are, let's say, x at time 0 is x0, and v at time 0 is v0, or let's call it x dot, initial velocity, then the response of this system has this form. X dot is equal to e to power of minus zeta omega n t, something like a constant, which turn out to be x0 cosine omega dt plus, this one was, I forgot, I guess we wrote the equation somewhere here, v0, okay. So that's v0 plus x0 omega n zeta divided by v0 or x0? Omega d. Omega d sine omega dt. This is what we had last time, right? That's the response of the system if zeta is less than 1. That's the case that we are interested. All right. So for the rest of them, the form of these equations was different, which we discussed them. And I guess this week your TA also will plot these graphs. The end of this module, there is a MATLAB code which you can plot this one. Nothing special about it. So this is where we got last time, right? So this response, if we plot it x as a function of t, we get something like this graph. And as you can see, the vibration starts from, let's say, x0, somewhere here, x0. Maybe it has a velocity or maybe it does not, depends on the slope. And the vibration becomes smaller, smaller, smaller until after some certain time, it gets to the original position or to the equilibrium position. All right. So if you look at these equations and compare them with the previous equation, which a case without damping, instead of omega d over here, we had omega n, right? So a system without damping, the sine and cosine, they had omega nt. But this time it is omega d, which also we defined omega d. We said omega d is omega n 1 minus zeta squared. And we call this one damping frequency. Right. So again, a system without damping moves ups and down with omega n, which depends only on k and m. A system with damping, it moves ups and down with omega d. So you can guess which system is faster. Like if you have two systems exactly the same, one of them with damping, one without damping, you disturb them the same amount and release them. Which of them is going to move ups and down faster? The damped or undamped? Maybe I repeat the question again. So we have exactly two systems, identical, one of them with damping and another one without damping. Right? We disturb these two systems a certain amount and we release them. So they're going to go ups and down. Which of them, if you just look at them, are they going to move ups and down together, or one of them is going to be faster or slower? Damping will be faster? Undamped, exactly. Thanks, Roy, right? Ray, sorry. So it's correct because always omega d is smaller than omega n, right? Because zeta is less than 1, that equation shows. So we know the definition of omega. So 2 pi Td is going to be less than 2 pi Tn. And obviously Td is going to be bigger than Tn, right? So it takes longer for a damped system to complete one cycle. So, and speaking of one cycle, I showed you Td here. From one peak to another peak, the time that it takes, we call it Td, and Td, we can calculate it using the formula that we have, 2 pi over omega d, and omega d has a relation with zeta. Also, you can guess from this formula, the bigger the zeta it is, right? The bigger it is, then omega d is going to be smaller. And so you know the relation. So something else that we are also interested in exploring is to see if there is any relation between, let's say, one peak to another peak. Let's call the first, let's say this peak, we call it x1, and the one after it, we call it x2. Okay. So x1 and x2, the peak. We know that the envelope of this equation that we just draw, this envelope, we know the formula for that one. It is e to power of minus zeta omega nt. All right. Why? Because if you look at our xt, we see these vibration things, the sine and cosine, it has been multiplied by another function, which is like exponentially reducing. So then this is our goal. We want to know if there is any relation between x1 and x2, or the ratio between them, or maybe there is nothing. So I can write down x1. So x1, which may happen at time t, or time t1, whatever we can call it. So we have the formula for that one. Let me write it down again. E to power of minus zeta omega nt x0 cosine omega dt plus v0 x0 omega n zeta divided by omega d sine omega dt. All right, so that's x1t, but or you can call this one t1, doesn't matter. So at time t1, let's leave it at t. Anytime it can be. So what about x2? x2 is going to happen at time xt plus td, because we've completed one cycle. So then the next thing is start at t plus td. So then our formula will be e to power of minus zeta omega n t plus td multiplied by x0 cosine omega d t plus td then we have the whole things here, v0 x0 omega n zeta omega d sine omega d t plus td, right? So I didn't do anything special. I just write the x1t, and then x2, it happens like at time plus td. We use the same equation. If we look at these equations, so td obviously is 2 pi divided by omega d, right? I have one omega d here, one omega d there. So it's going to be 2 pi and sine 2 pi, cosine 2 pi. So they are the same. So I ended up that inside brackets for x1 and x2, they will be the same. So if I write the ratio of x1 over x2, then it will be e to power of minus zeta omega nt, and here e to power of minus zeta omega n t plus 2 pi omega d. Let's simplify it. We will get e to the power of zeta. I have omega n. What else do I have? 2 pi and omega d. I guess so, right? Yes, that's correct. Okay, because we can simplify it like that. So let's simplify it one more step. I can write omega n as omega n, 2 pi, and omega d, I can write it as omega n, 1 minus zeta squared. So we ended up with x1 divided by x2 is equal to e to the power of 2 pi zeta 2 pi zeta 1 minus zeta squared, which is constant, right? x1 over x2 is e to the power of a constant number. If we repeat the same process, for, let's say, x2 over x3 and x3 over x4 and so on, we will get the same exact number, because if you just write the equation, the only difference between one to the next one is just that TD, and they cancel out. So we can write down then x1 over x2, they are all equal. x1 over x2, x2 over x3, and they are all equal to e to the power of delta. I just called this guy over here delta. 2 pi zeta 1 minus zeta squared. And this relation, it's called logarithmic decrease or decrement, because we say when we have damping, the amplitudes are going to decrease, as you can see with this function. Okay. So it looks like a lot of messy math, but it has applications. Can you guess any application for this one? So let's see what we get after. Let's say we have a system, it has damping, all right? We disturb this system. Let's say we can measure x1 and x2. If I have x1 and x2, then what value I can find from this system? So give it some thought. Let's say I have a system, and this system is a spring, damping, and mass. So mass, it's easy to measure it. I just put it on a weight, so I have M. K also is easy to measure because I apply some load, I measure the deflection, so I have the stiffness. The trouble is damping. So to measure damping, you need to have a system, a hydraulic, so you apply load with some certain speed. Measuring the speed is difficult, right? So anyway, measuring the damping coefficient C is difficult. Something that can help us is just knowing this formula. For example, if I know that, and by the way, in general, you can write down that xn over xm, just using that ratio that I wrote, is e to the power of m minus n delta. The ratio of the, let's say, second amplitude to 10 amplitude. It doesn't have to be just one after each other, right? You can find it using this relation here. So what we can find then, I disturb this system, and let's say by some certain amount. So I have x0. I release it. It does some cycles, and then let's say I measure the second amplitude, the third amplitude, and so on. So if I have the ratio of one of these amplitudes, let's say x1 to x2, then I can figure out what is delta, right? And if I have delta, then I can find out zeta, correct? And if I have zeta, right, it means, and already I know C critical because I have measured my mass and my stiffness, so I can then find out C. This is how people, in fact, they test the damping ratio. Your tutorial 3, the first question was a very common method that people measure their damping ratio for, let's say, a car shock absorber. So let's say with a car, many mechanics, they do it. So they apply some load, release the car, so it moves ups and down. They measure the amplitude. And if you know the amplitude of the ratio of the amplitude, you can find out the damping ratio. Okay. Confused or easy to understand? It's okay. Yeah. So when you are quiet. Okay. So one more time, let's see what happened here. For those who especially arrived late, what is this one? So we have a system with K, C, and M. We wrote the equation either by Lagrange or Newton. We got to this formula, mx double dot cx dot kx equal to 0. We define some values. We define the square root of k over m omega n. We call it omega n. We solved the differential equation and we found that there is this critical value that if that value change, then the behavior of the system will change. We call it C critical. We define zeta, and this zeta can be any of these 3 numbers, bigger than 1, equal to 1, and less than 1. Of course, it cannot be negative. It doesn't make sense. And when it is 0, it means we don't have any damping. Right? So it has to be one of these 3 numbers, either bigger than 1, equal to 1, and less than 1. Equal to 1 and bigger than 1, we call them overdamped or critically damped because it is right at the boundary. Right? So those are not that of interest for us because there is no vibration. You disturb the system, return back. So for a case when zeta is less than 1, this is the equation that we have, the standard form. We solve it for initial condition x0, v0, and we get to this long, ugly formula. Okay. So we don't need to know all the steps for the solution, but it's important to know that this formula is out there if we are interested in finding or plotting this function, the response, as long as we know x0 and v0. Okay, so, but it is important to notice few things about this equation. First of all, instead of cosine omega nt and sine omega nt, inside this bracket, we have omega d. So omega d, we call it damping frequency. It's always less than omega n. And we know that it's going to be a slower. TD is always bigger than TN. But something that we were curious to check was if there is any relation between x1 and x2, the ratio of them, or x2, x3, and so on. We solved this equation, we use those equations, we solve this ratio, and we simplify everything. So we got to this final equation. Yes, we found there is a relation, and that relation in general is xn over xm is e to power of m minus n delta. What is delta? It has a formula which is 2 pi zeta 1 minus zeta squared. Okay. Yes, right.
So when we divide x1 and x2 for 2 equations, does the rest of the formula does it come up to 1 when you divide the 2? Like the x naught.
No, they cancel out. So look at the inside bracket for these two. The only difference between these two equations is this TD, right, that we added. If you substitute TD with 2 pi over omega d, right, this omega d and this omega d, they cancel out. So you ended up with cosine omega d plus 2 pi, which is equal to cosine omega d. Like here, if I go over there, so you ended up with cosine omega d t plus 2 pi omega d, which is equal to cosine omega d t plus 2 pi, right? Which it is equal to cosine omega dt. So inside these two brackets are exactly the same and they cancel out each other. Yes. So I just, when you have these equations at the bottom, right? x1, x2, x2, x3, and so on, you can make it more generalized and say then xn over xm. N can be any number. Let's say the amplitude 10, and m is the amplitude 15. You can get them from this one, right? You just multiply these two together and you will see. For example, let me quickly show it here for you. So we showed x1 over x2 is e to the power of delta, right? And also we showed x2 over x3 is e to the power of delta, right? If I multiply these two, so I would get x1 over x2 multiply x2 over x3 e to the power of 2 delta. So x1 then over x3 is e to the power of 2 delta. Okay, so, and in general, we can say, as I wrote over there, xm over xn, you can have like that general form. Any other question? Good. Let's then solve some quick examples together. Example 9. So what do we have here? We have a system with mass m, stiffness k, and damping c. And as I said, damping or shocking absorber, we just show it by this, schematically by this shape. And the question simply asks, find out the critical damping for this system. So remember, we need to first find the equation of motion because we don't know what is the mass of this system. We don't know what is the damping ratio of this system. And we don't know what is the stiffness. We need to write down the equations, right? And see what are the, and compare it with our standard equation. This is mx double dot cx dot plus kx. So it's not always that we have m, c, and k. There might be different things here. So to solve it, you know what to do. You need to decide for a coordinate. Obviously, this system, the best coordinate can be a linear coordinate. And you decide for a direction. It's totally up to you. X, you disturb this system by some amount. You draw your free body diagram then. So if I move it by x, we know a stiffness is going to have a force, which is kx. And damping, we discussed damping, and we said always the opposite of the velocity is going to be cx dot. So we don't care about weight because weight probably the whole system, maybe it is on a table. Okay, so this system, or maybe there are some rails here and it moves on some rails. So this is our free body diagram. Sum of the forces is mx double dot, the Newton law, so minus kx minus cx dot is mx double dot. And from here, mx double dot, cx dot plus kx is equal to 0. Obviously, this system turned out to be exactly the same standard formula that we have. So question asks for C critical. C critical has a formula. It is 4 km. So it is 2,800. Right? And you know it has the unit Newton second meter. So this is a critical value for this system, because if the damping is bigger than this number or less than this number, the behavior of the system will be different. So nothing special about this question, just we wanted to review the formula for critical damping. So remember, critical damping, it depends on the value of K and M. All right. Let's take a look at example 10, which seems to be more interesting. Spend a minute, think about these problems, see how this mechanism works, and try to draw the free body diagram. And then we will solve it together. Oh, sure. Done? Okay. So try to draw the free body diagram and see what we need to do for this one. All right. So, free body diagram. You can, for example, so the variable the system decided to be X, but you can call like this angle theta and see how you can draw the free body diagram. Okay. All right, so let's do it quickly together, wherever you are. and we'll see how we can solve this problem. Okay, so the mechanism is obvious. We have this L-shaped bracket, or what did you call it? Crank AB. And from side B, we have damping C, or shock absorber C. And other side, we have mass M. Question says crank AB, we assume a small mass, so we neglect that mass. So we, based on the direction that the question showed, this X, we assume that the system moves that amount. So this mass M moved up, and therefore this crank is going to rotate like that. So this theta is going to follow X. But immediately we can find the relation between them, right? If because again, it's a small vibration, I can assume that if this angle is theta, obviously this one will be theta, and then I can write X, right, is equal to A theta. So that's the first things to make sure that this system doesn't need two variables. Still, it's a single degree of freedom system. And we are going to work with X. Second, we draw the forces. So we have this spring here. So the force is obviously Kx, right? And the other side, so there is a force that's resisting the motion. This mass likes to move up, but there are some force resisting it. We don't know what is that force. Let's call it F for now. This F obviously has to be on this diagram. Action and reaction has to be the same force that goes to that bracket or crank at that point, F. And on this side, I have the damping force, which is C multiplied by the speed. The speed of that point is B theta dot, right? Remember, damping, the force is always the opposite of direction. C multiplied by the velocity, which is B theta dot. So that's my free body diagram. If I get that part right, then the rest should not be an issue. So this is our positive direction, right? So that's X. So I will write the equation for this one. Sum of the forces is MA. So I have minus Kx minus F M X double dot. For the crank, AB. So since it's a rotating system, we need to use Euler equation. Sum of the moment about something that is the system is rotating about, O is IO alpha. Right? Question says this one is 0 because AB doesn't have any mass. Crank AB is weightless. So what I end up then, I will have, and the opposite direction for us is the opposite, the direction that I showed by theta. The theta direction. So I will end up then minus C E square theta dot, right, minus F multiplied by A is equal to 0. From here, I can figure out the value of F, right, which is minus C E squared over A. Am I correct? Seems correct. All right. So, sorry, somebody. Oh, yeah, theta. Let's quickly check the math. Seems to be correct. Yeah, seems to be correct. All right. So we have the value of f. We substitute it there and simplify everything. So I would get mx double dot plus c b squared a. Now I need to replace theta dot with x, right? So from here, theta is equal, or theta dot is equal to x dot over a. So then I would get here b2 a2 x dot plus kx equal to 0. Let's do it one more step. Mx double dot c b over a squared x dot plus kx is equal to 0. So this is my equation, differential equation of motion. So for me, the mass is m in this system, the stiffness is k, but the damping ratio is this new value. So this is the damping coefficient. So as you see, unlike the previous example, yes, please. We missed the minus somewhere? Okay, let's check. Oh yeah, you're right. Yes, yes, yes. This is positive. This is positive. Thanks. Thanks, Akil. And somewhere here. Figured the mistake. Okay. So this is positive. Please correct this one. This is positive. All right. So then remember, if a question asks to find the critical value of damping or something else, you don't know what is the actual damping value or what is the actual mass and stiffness. You need to always write the equation, and the coefficient of this one tells you what is the mass, what is the damping ratio, and so on. What this question asks to find? Okay, it asked to find something for damping ratio. So damping ratio, zeta, right? Zeta is C over C critical, which is 2 km. C over C critical, which is C over 2 square root of km. If I substitute those values here, I will get C B over A squared 2 km. That is my damping ratio set. All right. Question? So this is B over A, right? Here. But then we substitute theta dot by x dot over A. All right, I'll give you a moment to take notes, or if you have any question, feel free to ask. All right, so how do you guys feel about this sort of questions? Is it simple? You should be I guess you should be like you should be comfortable solving these problems. So by Friday, please take a look at example 11, 12, and 13. These three examples. I'm just going to quickly solve them the start of the next lecture. If you could solve them beforehand, that would be great. Then you could compare your solution with mine. Then do not forget, by Friday, please take a look at example 11, 12, and 13. Okay, see you on Friday.